this. This is a very good book. I think every one of us, we shall have a look into this. So what I expect out of this presentation or today's talk is a broad understanding of CBTC system and familiarity with the subsystems and technical jargon of CBTC. Let us say a typical signal engineer working on Indian Railways. If one of his friends is working in one of the metros on deputation, both of them shall be able to talk on telephone, voice communication without misunderstanding. That's what I mean is technical jargon. Some of the metros are Indian Railways with CBTC. Hyderabad is with Thales, Lucknow, Kochi, Mumbai yet to start, Jaipur are with Alstom, Ahmedabad and Delhi are with Nippon, Mumbai, Kolkata, Ansaldo, Delhi, Nagpur and Pune are, Delhi is Bombardier and Nagpur is with Nagpur and Pune are with Westinghouse Siemens. Bangalore, first phase and Chennai are not CBTC, but they are distance to go. We will be just discussing a little of that. Bangalore phase 2, I think they are going for CBTC. What is the difference between mainline signaling and metro signaling as far as operations are concerned? So average speed, mainline is about 50 to 75 kilometers. Metro is 30 to 35. Headway is 5 to 7 minutes in the busiest routes in the main line. And in the metro, it is in seconds, maybe a minute, 1.5 minutes. Interstation distance are 6 to 10 kilometers, and here it is hardly a kilometer. Braking distances are very less, almost about 200 to 250 meters. Station yard layouts, for the passengers' sake, there are no yards practically, very few lines will be there, only 2 lanes normally. Only in the yard depots, yards are there. Signal clearance may take some time because it is done manually in main line, whereas it is a question of seconds. Then stopping time at stations, 2 to 5 minutes per main line, whereas it is in seconds in metros. So distance between 2 trains is absolute block system. We are having about 6 to 10 kilometers. Auto signaling, it is hardly a kilometer. Whereas they can be as less as 25 to 30 meters in metros. So what made it possible in metro, the standard talks about? We can say train controlling has 2 types. One is external to train, other one is internal to train. External to train, we are all aware. When we start from the beginning, the first time interval system was there, and then it became space interval. Time interval was not safe because if the train ahead gets braked, there can be collision. That is why we have gone for the space interval, where human agencies are responsible in the beginning for avoiding the collisions. This is how the signaling solutions we are providing. Let us see the blue portion first. There is a single line. Now to increase the line capacity, the civil engineering solution of a crossing station, of course, with signals was provided. And then again, if the traffic is more, going for the double line. And then later we have signaling solutions which without infrastructure of civil engineering, the providing the IBS and then auto signaling. But later, to help the operator, we have developed the TMS, CTC, and then ETCS are the latest standards. This is the conventional train controlling, where a controller, traffic controller on telephone advises to the station masters at the stations that which train has to be preceded or where crossing has to be arranged. This is the indirect way of controlling the train. Then came the TMS. Basically, TMS, it is a tool for traffic controller. It is a real-time display of train and a mimic diagram with train numbers also displayed, so that the controller has an overall view of the situation. The background work involved is train tracking, which require train number entry also. If it is done, train number is displayed. Then train charting, automatic charting, where the delayed or on-time trains are also shown. Then integration with crew and rake management, loco management softwares makes it optimization of the resources.
Sir, 1 minute, sir. Sir, actually,
Yeah.
the slides are coming a little bit slow. So you can
Oh.
give a slight pause after every slide, sir.
Oh. Now it is TMS is available with you. TMS train management
Yes, sir,
system.
it's visible, sir.
Yeah, it's fine. It's fine.
Yeah, fine, working fine, sir.
Okay. Yeah, next one you got?
Yes, sir.
CTC.
Yes, sir.
Centralized traffic control.
Yes.
This is here actually there is automation in train controlling. Automation happens in route storage and then automatic route setting. These are the two features which makes the automation possible. That is, interlockings are controlled from the central place by the CTC machine by a central person. If we look at how the signaling systems have evolved, we can say first signals starts detecting the point. So signal engineer is exposed to the track. He is supposed to have knowledge of points and crossings. Then came the train detection with the track circuiting. So the insulation properties of the track, sleepers, those knowledges are required. Then came the repetition of the signal aspect into the cab. So here the human element is now involved, that how the driver looks at it, how he responds to it, and in the cab. We had number of cases where they were even damaged in the initial stages because they thought it is a not an aid, but it is a snooping their activities and all. Then we have controlling of brakes and then controlling of the propulsion. Propulsion means actually deceleration and acceleration, stopping and speeding of the trains. Now we are supposed to know the loco characteristics also as signal engineers. So the same thing we can show in a different way. We can see who is our consumer. The consumer of the signal is the driver in the beginning. So track circuit point LC gates form a route and then a movement authority is generated and shown in the form of signal and the train driver used to consume. Now the movement authority is consumed by the train directly. So the knowledge of the train, loco, propulsion as well as braking is a very, very important thing for signal engineers now. Let us have a look at the speed profiles of the trains, how they are shown. In the top graph, we can see it is called the static speed profile. A speed restriction is there. And of course, as the train comes to the signal which is showing to the red, it is supposed to come to stop zero. Y-axis is the speed, x-axis is the distance. Actually, here it is shown as if the train speed has to reduce from x to x minus y. It would happen in a sudden way. There is a braking characteristic. This is called dynamic speed profile. So the dynamic speed profile is the thing which really important for us. Train speed is controlled in two ways actually, or two considerations are there. It is based on severity of speed deviation. That is, at a particular location, how more is the speed than the permitted one. That is the severity. Other one is based on the distance, how to reduce the speeds in steps. These two. Let us see in the form of again diagrams. This is talks about the severity. That is, the bottom one is the dynamic permitted speed. If the speed goes beyond that, the second graph, warning speed, it is still permitted. Then if the speed goes beyond that, the third one, automatic switching off of power to the motor happens. And then the service brake, even if it goes beyond that, service brake is applied, and in the last, it is emergency brake. So this is the dynamically how the severity of the braking occurs or controlling occurs. This is how gradually it can be seen, like speed can be controlled. It is Japanese ATP. You can see the SS is the place where it is supposed to stop the train. So there are S1, S2, S3, S4, different distances. The speeds are advised to the train, and train is supposed to control its speed on its own. So this is the Japanese system. The well-known the train TVM 300 of French. This is the speed profiles, how the speed is supervised. There are different steps at different speeds. Now, how the train is controlled to maintain the safe distance between the trains. Distance to go is one type of train controlling. In this, AFTC carries the train information to the AFTCs in the rear. Here, train 1 and train 2, two trains are there. Now, AFTC 4 gives the status of the train 1 to train 2. The transmission takes place through the wheels of the train. This is actually the distance to go has a disadvantage that it can come and it comes and stops at AFTC 2 and AFTC 1 border. It cannot enter into AFTC 1 even though there is a lot of space in AFTC 1. So ERTMS, that is European Railway Train Management System. This is the one, it is becoming world standard and we are also adopting in India. So it has two parts, ETCS and GSMR. ETCS is the signaling component, GSMR is the telecom component of the ERTMS. Let us have a very brief look at it. Why Europeans has gone for ETCS? Main reason is interoperability. This diagram shows a loco which is fitted with various sensing units of various train controlling systems prevailing in Europe. You can see a number of them, tens of them are there total if you see. So it is if a train has to travel from one country to other, now in Europe trains can be, country can be passed in 3 hours, 2 hours. Then it is going to be very, very difficult to make use of the train protection systems provided in that country. So the ETCS was the requirement for them. Now, how the information is transferred from the signal to train? It is the Euroballis. What we are seeing between the tracks is called Euroballis, and this is the receiver, which is fixed below the train loco. Of course, there are other means also we can see later. This is ETCS 1. The first system is simply it conveys the signal status to the train, and the train applies the brakes if the eventuality of passing the signal at danger arises. Here you can see there are only two additional things provided. The brown one down below, Euroballis, and LEU. Line side electronic unit takes the aspect of the signal, feeds to the Euroballis, and when the train comes over it, the EVC, that is vital computer, European vital computer, receives the data and then applies the brakes. Now, what you are seeing here is one ballis, but there will be number of ballises ahead also. That is at 1 kilometer, maybe 0.5 kilometers. That is infill ballises, they are called. So this is the basic system actually. This we have provided in Agra to Delhi section and then Chennai suburban also in India. This is the second one. Now you can see here LEU has disappeared. Now the interlocking is giving the status to the RBC, radio block system, then that is sending the signal aspect through wireless, that is GSMR, to the EVC. So the EVC now does whatever is the job, but still Eurobalance is here. This Eurobalance is a passive Eurobalance, it only gives the status of the location of the train in a fixed information. Why it is required and all we will see later. Now, here the train detection system also is removed in the ETCS3. In the previous one, line side signals are eliminated, but train signal detection system has remained. In system 3, the train detection system also is eliminated. That means train itself communicates that where it is to the RBC. Then RBC decides to what extent movement authority can be given. This is the comparison of various levels. Actually, this can be seen later also after the presentation. My intention is not to really explain all these things, but to be made available for you. Now let us look at the CBTC. Why CBTC? CBTC is actually being used for mass transit, metros only. So the less line side infrastructure is more reliable, but this is debatable. We will discuss later why it is debatable. Easy to and maintain, and better train control because of the precision of the location identification, and more line capacity creation with the same infrastructure. So less maintenance cost and more availability because of the diagnostics and then standby systems provided. Now, generally about IEEE standard. These standards are made by IEEE Standards Association. It is under Standards Board, and all the members are volunteers. They need not be members of IEEE. They follow the process approved by ANSI, American National Standards Institute, this American system. Then IEEE do not evaluate or test or verify any accuracy of the standards. And use of IEEE standard is voluntary. So this present standard is made by IEEE Vehicular Technology Mission and Rail Transit Interface Standards Committee. So it is not mandatory for a product to be declared that it is as per IEEE standard. Now IEEE standard 1471, actually it is 74, it is wrongly written here. 74 has 3 parts, 1, 2, 3. That is performance and functional requirements, it says number 1, and user interface, which is small 1. And third one is recommended practices for CBTC system design and how the functions are allotted to each subsystem. These are the 3 parts actually. This presentation is about part 1, and part 2 and 3 will be the next presentation. Maybe it may take about half an hour to 40 minutes. So we have seen already features of CBTC in general. So high precision train location detection by train board system. The train itself detects its location. Transmission of train location to wayside controller. Then again, wayside controller generates a limit of moment authority. And again, fourth is again communication back to the train-borne system. And then implementation of moment authority by train-borne system. So basically, this is the system actually. Now, if you look at the functional part subsystems, we can say there are 4 systems actually, subsystems available typically. One is train-borne CBTC equipment. Then other one is CBTC wayside equipment. And third one is the automatic train supervision. And then data communication system, of course. Auxiliary wayside system is optional actually. Now, this is what is provided in the car-borne CBTC equipment, what is provided on the logo. This is the zonal controller or the wayside equipment. It's nothing but electronic interlocking with more facilities. Like instead of track circuits, it can precisely make use of the location of the train for the purpose of movement authority. It can operate points. It's like any electronic interlocking. That is the features of this. Please have a look for 10 seconds about this diagram. I will just explain after 5 seconds. So here we see, first let us see car-borne controller, CC. It is connected to the various subsystems like TIA, tag. It is about the reference of the position on the track where it is. Odometry devices, exact location of the train, TOD, which is the train driver's operator's display. And then the other one is the train subsystems like braking and acceleration, door controls, all those other functions of the train. These are the things. And it is connected to 3 systems outside. One is automatic train supervision, you can see on the top. And the other one is auxiliary warning system. It is optional actually. Third thing is the zone controller. Zone control is like electronic interlocking. Auxiliary warning system can be anything, any other train protection system with agile counters or AFTCs and regular signals also. And then automatic train supervision is a software and which implements the timetables and scheduling of the trains. Now we have 2 ellipses we are seeing here. Vertical ellipse is a radio-based network. That is because the train is a moving thing, it has to communicate with the ground through wireless. So it is done through wireless. And the other one is ground-based network. How the subsystems within the station are connected to each other. They are all connected through wires. Now,
Nippon Signal CB.
Now this about 5-6 minutes, you can have a look at how Nippon Signals has implemented CBTC and Delhi Metro. It is made for the Delhi Metro by Nippon people. It gives a fairly good idea about the subsystems and then moving block feature.
CBTC Sparks. Communications-based train control. CBTC is a new train control system achieved by wireless data communication. CBTC is rapidly becoming a mainstream train control system for urban railways. By relying on wireless communications, CBTC reduces initial cost, running cost, and maintenance cost. Now Nippon Signal has created its own version of CBTC called Sparks. Let us now introduce the system configuration of Sparks. Sparks consists of 4 wayside signaling systems. Sparks Station Computer, Station Radio Set, Wayside Radio Set, Wayside Balise for position correction, as well as 2 onboard signaling systems. Sparks onboard equipment, and vehicle radio set. Sparks Station Computer delivers highly reliable data processing using fail-safe logic circuits and high fault tolerance against unit failure. Station radio set is physically connected with Sparks Station Computer by a signaling cable. Communicates with wayside radio set and vehicle radio set by radio transmission. Wayside radio set communicates with station radio set and vehicle radio set by radio transmission. Since no signaling cable is required, Wayside radio set is easily installed. Each Wayside radio set is allocated in a good distance where it can communicate with each radio set after the next. The Sparks onboard equipment controls automatic train protection, ATP, and automatic train operation, ATO. ATP control logic and ATO control logic are combined and integrated. Vehicle radio set is a radio device installed on top of train cars. It communicates with station radio set and Wayside radio set by radio. And with the Sparks onboard equipment, the cable is used for communication. Sparks employs a combination of two methods to detect train position. The first method uses balises for position correction and a tachometer generator. When it passes over the balises for position correction installed between stations, the Sparks onboard equipment receives positioning data. This reception triggers the tachometer generator to measure a distance. The second approach is radio ranging, a unique feature of Sparks possible only by radio transmission. Train position is detected by calculating radio transmission time between Wayside radio sets and vehicle radio sets. This method instantly detects train location, even immediately after system startup. Sparks Station Computer compares the train location information from these two distinct sources. If they match, Sparks confirms the train location information, providing highly reliable train location detection. We now turn to the train control method. The Sparks onboard equipment generates a brake checking pattern to prevent collision with preceding trains. Train speed is constantly monitored to ensure safety. Train speed exceeds that of the brake checking pattern, the automatic brake is applied. Sparks generates moving blocks. With conventional fixed blocks, succeeding trains cannot enter a fixed block ahead until preceding trains have completely departed. The moving block generated by Sparks responds dynamically to the departure of a preceding train. The succeeding train can proceed as long as it maintains a safety margin with respect to the preceding train. In this way, Sparks can shorten the headway of trains. Sparks satisfies unattended train operation GOA 4 as stipulated by the IEC International Standard. Departure and arrival of trains, control of doors, and control of platform screen doors are all controlled automatically by Sparks. In China, Sparks has been in operation on the Line 15 of the Beijing subway since December 31, 2011. Sparks is also certified under SIL 4, a safety certificate under IEC.
This small video, I think, must have given you a good idea about how the CBTC works. Now let us have a look at performance and functional requirements of the specification. The first, limitation of the conventional system. The resolution of train detection is limited to track circuit section. And information provided to train is limited actually. Few signal aspects are small number of speed codes through AFTCs or whatever. Enforcement of movement authority by wayside signal is intermittent. We are not talking about ETCS 3, but we are talking about conventional systems available till now. So characteristics of each CBTC: train location determination to higher precision, independent of track circuits, continuous data communication between train and wayside, and implements continuous ATP, ATO, and ATS. Let us see what they are. So benefits are closer headways, greater precision, continuous safe truss operation, and overspeed protection. Now there are about 6 classes in this. Out of that, we will be looking at 4, 5, 6 only. Remaining things are just casual things. General requirements, performance requirements, and functional requirements. Now let us have a understanding about ATP, ATO, ATS. But all three put together is called ATC. Automatic train protection is a fail-safe thing. This is supposed to avoid the train accident due to collisions, overspeeding, or other hazardous conditions like over the points and through train detection, train separation, and interlocking. These are the three things. Automatic train operation is automatic speed regulation actually, and automatic stopping also, acceleration and deceleration, as well as train and platform door controls, the facilities available within the train, controlling of those functions. Then automatic train supervision is about the monitoring and scheduling of the trains, how the trains are, that is the TMS portion of it to some extent. Minimizing the inconvenience to the passengers or the services in case of a failures. All those functions are done by the automatic train supervision. Basically, automatic train supervision and automatic automatic train control is combination of ATP, ATO, and ATS. So this is the platform doors of the metro, and then the doors of the train itself is different. So this is just for the people who may not be knowing what is automatic train operation. So both these are controlled by the ATO. So in these general requirements, it says about characteristics of CBTC, categorization, range of application, train configurations, train operating modes, entering and exiting of CBTC territory, train operating speeds.
उसका क्या रिप्लाई? हाँ सर खुल गया, तो पासवर्ड वगैरह लिंक से ही खुल गया वो.
Characteristics of
तो लेटर दिए, हाँ चल तो रहा.
train location determination, higher precision, and bidirectional high capacity data communication, train board, and wayside processors. Categorization, we can say the CBTC can function only ATP also. It can be limited to only ATP, and it can do partial jobs of ATP and ATS. And it need not be the only control system. It may be working in conjunction with other auxiliary wayside system also. This is what I said in the beginning, that less equipment is not happening in real times. CBTC by itself may have less equipment, but when we are depending on auxiliary wayside systems, we are providing track circuits, we are providing AFTCs and signals, and again electronic interlocking. So it is actually the double system. So the same diagram is shown in a little different way, functional block diagram. So train-borne CBTC, train operator controls and train subsystems of brakes, doors, and other systems. On the top, that is wayside equipment, that is called the zonal controller, and then it communicates with the adjacent zonal controllers also. And this is the auxiliary system. Interlocking is optional. And then ATS system. ATS is software basically. Train configurations, actually CBTC is supposed to support unidirectional, bidirectional, fixed length as well as variable length. Maybe we are thinking that it is used on metro, so it has to be only 3 car, 6 car, 9 car like that. It need not be. So mixed fleet trains also it is supposed to cater by design with different performance characteristics, like with different braking distances and all. Train operating modes. In fact, this is not exactly part of the spec. This is not provided in this standard, but this is interesting. It's a very important thing. So, grade of automation. There are 4 grades you can see here. The one is where the driver with attention. So, ATP will be working, but he will be doing starting of the train, stopping of the train, door closures, operations in the event of any disruptions or any problems. Similarly, in GOA 2, the next level, ATP, that is train protection and the operation, are with the driver actually. That is ATO and ATP are done actually. The train starting and train stopping is done automatically, and only the driver does the door closure and then other. GOA 3 is practically driverless. Only some attendant can be there. Is required maybe because for door closures or operations in case the train stops in somewhere in the middle, he can coordinate in restoration. The last one is the unattended train operations, where even in case of emergency, the system is supposed to take care of things and then start the train. So train operating modes, CBTC equipped trains, that is with full protection, and non-CBTC equipped trains, that is auxiliary wayside system protects those trains actually, CBTC won't protect. So failure mode train operation in CBTC territory, because in case of failures, how the trains have to be dealt. So there are degraded modes. So it can be achieved through functional elements of CBTC itself can have standbys and it can take care of it, or auxiliary wayside systems can do that. And combination of both also it is possible. So the failures can be of 2 regions. One area completely may be affected. So the other one is one train in a control area also can be protected, can fail actually. So in these cases, protection of auxiliary wayside system also can be deployed, or through the operating procedures, that is the rules implementation or combination of both. So it is one area of control failure or one train in any area failure. So if one train fails in an area of control, it works on the protection of auxiliary wayside system. So train speed is limited by propulsion system itself. That is train speed still can work many times even without auxiliary wayside system also. It depends on the failure modes. So in CBTC train operating modes in the non-CBTC. So the CBTC trains can go into the non-CBTC territory also. So it shall cater for transition into CBTC territory. In this, what happened? Actually, it should know. The equipment can still do some functions like limited train speed and zero speed detection. These functions can be provided even in non-CBTC territory also, because it is available in the car-borne controller. And sometimes even the standard permits that this CBTC can be integrated with the other system, and indications can be provided separately or can be integrated depending on the user's requirement. So interoperability or the directly within the CBTC system, they are not talking, but they are talking about the integration of CBTC with the other train protection systems. So failure mode in non-CBTC territory, if the CBTC equipment fails, it doesn't have any impact on this train. Entering and exiting of CBTC territory. Actually, the CBTC equipment gives precise knowledge of limits of CBTC. So verification checks are done much before. So before entering into the CBTC territory itself, verification is done, and then there is no need to stop before entering or exiting. If at all there are any failure results, they are displayed both to the ATS operator in the central place as well as the train driver. Exiting also, visual indication to train operator is given, and there is no need to stop. And the CBTC knows the new control system, it may display those aspects also if it is exiting the CBTC and entering other systems. It's something like this. So CBTC to no CBTC and no CBTC to CBTC entries are supposed to be transparent. There should not be any stoppage of the trains. Train operating speeds. Even though the CBTC is provided on the mass transit systems where speeds can't be more than 60-70 kilometers, the standard says that it shall cater for the full speed, any full range of train operating speeds. Performance requirements. So CBTC factors which contribute to the achievable headways and trip times. So let us see only these two things we are going to cover in this. Safety requirements, system assurance requirements, environmental requirements. These are all typical things for any products. That's why I'm not covering these three. Safe train separation requirements and safe braking model. This is the thing which decides the headway. So two types of headways can be arrived or can be given by the CBTC. Uninterfered, that means trains are allowed to go at their maximum permitted speed. So naturally it gives the minimum trip time. Second one is the interfered ones. That is, the train speed profile is affected by the train ahead. So the ahead train is made to go slow. This train is going to be affected if it is programmed by the operator. So it is the interfered model. So that is, if we have more number of services, if we want to run, then we push the trains one behind the other. So that increases the trip time, but it increases the number of trains, most probably. So what are the CBTC factors contributing? These 6 factors shown here, they are the outside the control of the CBTC, like track alignment and gradients, civil speeds, acceleration and braking rates, which are of dependent on the engines. Station dwell time. Dwell time is the stop time actually, and terminal track configurations, how the terminal yard is designed, and driver reaction times. These factors cannot be considered for the CBTC by the CBTC. What are those factors that contribute to achievable headways? The accuracy of the end of the train location. So it gives a very good resolution of for the movement authority limits. So thereby the trains can be taken closer, and also frequency at which location reports and movement authorities are updated. Typically, they are given at 0.5, 0.6 seconds. Each train gives its location to the central location. So these two makes it more what we call the head reduces the headways actually. Then speed, accuracy and resolution, communication delays between the wayside and the train. Then CBTC equipment reaction times. These factors we will see actually in the next slides how much they are. Then CBTC system performance limitations and CBTC automatic speed regulation algorithm. These are the things which contribute to the better headways. So these are the times, the limitations of whatever is the typical range of the things. So each zonal controller or wayside controller, you may consider it as a station. About 10 to 40 trains, it shall be able to consider. Station doesn't mean the passenger stopping train. Maybe because trains, stations are every half a kilometer or even kilometer sometimes. So 3-4 stations can have one zonal controller also. Resolution of measured train location for the ATP purpose, 0.25 meters to 6.25 meters. Accuracy, 5 to 10 meters. Similarly, accuracy of measured train location for programmed station stop. Station stop is a very, very important thing because the train cannot go beyond the platform. That is why it is made to 0.25 meters. For this purpose, additional gadgets are deployed. The accuracy of the same for the measured train location is 0.05 meters for the platform doors purpose. These the platform edge doors. Platform edge doors are the ones which are provided on the platform, whereas the platform doors, actually train doors are 0.05. Then movement authority limits, 0.25 to 6.25 meters. Resolution of train speed, 0.5 to 2 kilometers. The accuracy of train speed, plus or minus 3 kilometers. So resolution of train speed commands, 0.5 to 5 kilometers per hour, depending on the application. Anything can be chosen. Up to 0.5 kilometers increments can be given for the train speed commands. What we have seen in the earlier slides, where the speeds are reduced in steps or increased in steps. So this is the one which matters actually, 0.5. Train to wayside and wayside to train delays, 0.5 to 2 seconds. Wayside CBTC equipment reaction times, about hardly 0.07 seconds to 1 second. So these are all the recommended typical ranges actually. Again, rollback detection, 0.5 meters to 2 meters. Then zero speed detection criteria, less than 1 to 3 kilometers per hour for 2 seconds, 1 to 3 kilometers per hour. So trip times, because trip times and headways are both interchangeable. So here there is nothing much actually to discuss because trip times are affected the same way as the headways. Safety requirements, system safety requirements. So these are the things which we have covered. System assurance requirements. Things. Environmental requirements for any modern systems, they are similar, so that's why I'm not covered. And functional requirements. So we said there are 3 types of functions that are to be done for train controlling: automatic train protection, operation, and supervision. And of course, interoperability of interface requirements also are there in the functional requirement. So ATP, ATO, and ATS, all 3 functions are to be provided. ATP is a fail-safe function, and it overrides the ATO and ATS. So ATO operates its own on its own. It operates the functions. Otherwise, it is operated by train operator. That is GOA 4 to GOA 1. Complete thing it should support. ATS provides the system status information. It means same the tracking of the train, those informations, and these are supposed to be displayed actually in the ATS, and then it controls, sends the commands where crossing is to be arranged, or not crossing, actually precision sensitive anything, or reduction of the speeds, all those things. Then here, even automatic control can be overridden by the ATS because bidirectional data communication to support this. So speed to support defined performance requirements. Performance requirements given earlier, the speed is important. Then here for data link means it includes the protocol structures to support the safe, timely, and secure delivery of train control messages. Encryptions and all those precautions are supposed to be taken. So train location and the speed determination. So it is supposed to locate the train location, speed, and direction, and both front and rear. This is very important things. This is one which gives the integration of the train. Train integration is proved by both front and rear. And it shall meet resolution and accuracy parameters what were provided earlier in the table. And CBTC train detection shall be automatic actually. When a train enters into the CBTC section, shall not be any human entry saying that yes, recognition of the train or things like that. It shall declare by itself and then get automatically integrated into the system. So it shall compensate for, we are talking about train location actually. So it shall compensate for measurement inaccuracies like slipping of wheel, sliding of wheel, wheel wear. Slipping of wheel happens when adhesion is less. So the train wheel rotates there itself without travel. So this increases the odometer's reading wrongly. Sliding of the wheel. Here, wheel won't rotate, it slides in case of braking and all. So this one reduces the actual distance. The wheel wear. Wheel wear increases it has increased effect on the distance traveled. Wheel wear happens in case generally during the braking. So a portion of it becomes flat. So that is actually machined in the workshops and thereby reducing the diameter of the wheel. So the wheel wear becomes a very important safety parameter in case of train localization. Secondary train detection. So track detection. So track detection, accuracy by occupancy by a CBT2 train or failed or non-CBTC trains are detected. That is, if we provide AFTC, it detects a train with CBTC facility and a train without CBTC facility also. But accuracy of location, CBTC train has an advantage. It can very clearly say that on which portion of the track in the same section it is there. So secondary train location determination we can see in this. So the borders given here of the actually it can be AFTC or axle port. You can see if both the trains are with AFTC, train 1 is shown in this blue envelope. CBTC recognizes exactly the train portion which is occupied by it. Similarly for train 2 also. Now you can see here the first train, that is the ahead train here, has a failed CBTC or maybe without CBTC. Now the CBTC equipment detects it as if the whole track section is occupied. Whereas the following train, which is a T1, where its own CBTC is working, it is detected as if only this particular portion is occupied by it. So you can have a look at this diagram. Now here, both the trains CBTC system has failed. That is, train it could not locate its position. The disappearance of this Blue envelope means that CBTC is not working. Now here, the axle counter or track circuit section says that the train is anywhere in between in the track section. So the vacancy is now seen by the CBT system as if it is between the two boundaries. So we are not able to make use of the distance up to the end of this train or beginning of this following train. So it is a derated or degraded operation where trip times are affected and then headways are affected. Functional requirements of ATP functions we are looking at. Now, safe train separations. The system says safe train separations are to be provided for all types of trains. That is CBTC, okay. In case of any problem or any unsafe thing detected, it shall provide instantaneous stop of the previous train. Mixed mode operation, that is auxiliary wayside system also it shall be able to make use of. So movement authority of a CBTC train following a failed or non-CBTC train, what example we have seen is limited to the boundary of track occupied the failed or non-CBTC train rather than up to the end. In case there is a yard, big yard, and big station, and there the train is entering, and in such case, the permission is given only up to the route entry point, because here the route may have more than 2-3 track circuits involving given points. In such case, only beginning of the route up to that only can give movement authority. So train with CBTC equipment, train without or failed CBTC equipment. So the movement authority can go only up to C. So functional requirements of ATP. So safe train separation. It consists of actually how the safe train separation is provided. Calculation of a ATP profile. It is derived from fixed ATP data like permanent speed restrictions and variable ATP data. That is the temporary speed restrictions which may happen during the servicing time, and the movement authority limit also. Movement authority limit is generated by the train ahead. That is variable again. So supervision and enforcement of ATP profile also shall take place based on the A above. How is movement authority limit decided? There are number of cases, like most restrictive of the following essays. Rear of the CBTC equipped train ahead. It is a normal course, it happens like that. A CBTC train is going ahead. Movement authority can go up to the rear of the CBTC, of course, taking into consideration those limitations, error for the limitation and all. Boundary of the track section occupied by train, which is having a failed CBTC or non-CBTC. Number 3, end of track at la terminal station or in the station in between also, where the platform is ending there itself. Number 4, entrance to an interlocking when route is not locked, because CBTC system can do all the interlocking functions by itself also, but there can be cases where conventional interlocking, electronic interlocking is used and it is interfaced with the CBTC. In such cases, entrance to an interlocking up to that CBTC can give when route is not locked by the electronic interlock. Boundary of a track section with opposite traffic direction established. Here the isolation is not like in conventional railway systems. So the trains can come in opposite direction within up to the safety limits. So if a particular track is designated to receive a train in the opposite direction, still to the adjacent track circuit we can send the train from the opposite direction. Then boundary of the blocked track. Then entrance to a route when the route is not safe, like it is not locked, let us say, and point failed. In case of level crossing, when the warning devices are not functioning, then up to that boundary of the gate. CBTC shall also provide abnormal movements like coupling, uncoupling, closing up of the trains. It shall be possible. And it shall be also possible to bypass safe train separation when the train is driven manually for failure recovery. In case of a failure, again, it shall not create a deadlock. It shall be possible to bypass this. And like putting back the signal to danger, facility to pull back the movement authority also shall be available. Safe braking model. What are the considerations? Because safe braking model is very important thing. So location uncertainty of a lead train, including the rollback tolerance. Rollback of 2 to 3 meters what has been given in the parameters that also to be considered. Then location uncertainty of the following train length, train configurations, allowable speed permitted by the CBTC system, then maximum CBTC speed measurement error, CBTC system reaction times and latencies, worst case latencies are to be considered. Further, maximum train acceleration rate possible at the time of detection of the overspeed, at that speed, at that location. Then worst case reaction times of disabled propulsion, that is the engine, and applying of emergency brakes. How much worst case, how much time it takes for applying of the emergency brakes after initiation. So guaranteed emergency brake rate and then gradient of the thing. So it shall, CBTC system as per the standard, it shall support multiple safe braking models to accommodate different train acceleration and braking rates. So it is not limited to metro trains, it can have goods trains also and express trains, normal metro trains also. So it also shall ensure correct safe braking model is applied for a particular type or class of service and at a given location. So this matching also has to be done. For a goods train at a down gradient and when the adhesion is less while raining, the model has to be selected based on that, like that. The standard says that it has to be selected like that. Now this diagram gives us some idea about how the safe braking model is there. The green one is basically the ATP profile. Within this, the train is supposed to run. In case overspeed allowance is there, this is the allowance between the dotted red and green. This is the allowance provided. So within that allowance, also it can function. Then comes the third case where emergency brake curve. Here actually you can see the lot of steps, but it has been expanded for the purpose of understanding. Really, it won't be like this, it is not as per the scale. So it says first, this A portion, if you look at, is the train-bound ATP reaction time. It detected that yes, emergency brake has to be applied because the speed is at this particular level. Now, this is the one which takes time. Then emergency brake initiated by the ATP at this particular point. And then B is time to disable propulsion, that is cut off the power to the loco after the initiation of the emergency brake. So this is additional time they have catered for the application of the emergency brake. D is the one emergency brake build-up time, and then E is the one which says that the emergency brake application is effective from E onwards at this particular rate of deceleration. So when this happens, it still shall end up sufficiently backside of the train ahead, which says which caters for the position uncertainty, PU. It is position uncertainty has two factors: rollback as well as the accuracy of the measurement of the location. So what is safe speed? How to decide? So most restrictive of the following ones: permanent speed restriction within the ATP speed profile. If permanent speed restriction is more than the ATP speed, we can start. For example, ATP speed profile says the train is ahead, so it has to go at 30 kilometers. At that location, the speed is 70 kilometers PSR. It need not bother. Temporary speed restriction similarly. Then PSR for the class or classification of that particular train. Let us say the maintenance train only has this particular speed restriction, but regular train services need not have. Speed restriction, the item number 4 is speed restriction imposed on the train because of the train-borne failure. Let us say CBTC equipment has failed, so the train can work on auxiliary system, but its speed is reduced. Maximum speed that allows a safe stop prior to a movement authority. This is the main thing actually. Maximum speed that is allowed to stop at the end of the movement. Braking. So what are the types of brakes? There are two types of brakes are considered here. One is service brake. It is a non-emergency brake application, which is reversible. That means after application of the brake, if the conditions permit speeding, it shall be able to come back to the normal speed. Emergency brake, it is a fail-safe one. So it is supposed to have assured maximum stopping distance, and this brake is irreversible. Once emergency brake is applied, unless the train stops, it cannot be reversed actually. So normally user specifies. Service brake can be first applied if the braking rate is not achieved, then emergency brake can be applied. Something like the algorithm can be decided by the user. When we say the user here, we are not talking an authority actually. We are talking about a technical consultant, including the user, both together actually. It is not an administrative type of a decision. So rollback protection, there are the 3 steps actually. So actual train travel direction, and it is compared with the travel direction of the movement authority, and the travel of the train in the opposite direction, how much. These are the 3 factors actually. So we have seen 0.5 to 2 meters. It can go. If it is trying to go beyond that, then the emergency brakes are applied. End of the track protection, in case buffer stops are there, this is a part of a overspeed protection actually. So this is about the part that consists protection and coupling and uncoupling of the tracks. So a train can be formed by coupling together of 2 or more vehicles, and it can detect the parting also. And when both the trains are coupled, it shall treat both of them as a single entity. And the new length of the train also it shall update to the user, the ATS user. And sometimes user can say that, okay, in case train length is missed, that you can take this train length as a fixed length of say 686 meters is the length of the train, or 500 meters. That also can be given. So we have seen other one, zero speed detection. So less than 1 to 3 kilometers for 2 seconds if it travels, it is treated as a zero speed detection. Then ATP functions coming to door opening and control protections. So trains operated with cruise and without cruise. Without cruise, it is mandatory that door opening and control. With cruise, it depends. User specifies whether it requires manual or automatic. So train should be properly aligned at a stopping point. There is platform on the proposed opening side, and zero speed is detected. These are the conditions. And the train is constrained against motion, and selective door opening. That is, if the train length is more than the length of the platform, only the portion of the train which has access to the platform, it shall be opened. And local bypass facility, of course, in case of failure. So departure interlocks. This is mandatory for train without cruise. And a stationary train from moving, unless all doors are closed, it shall not happen. And of course, manual bypass is there. So emergency braking. Emergency braking can be reset also. But after the reset, again, if the train speed exceeds, then again automatically reset is applied. This is what the standard says. So route interlocking. Actually, CBTC system does exactly what conventional interlocking does. It can operate the points, sets the routes, the complete functions of conventional interlocking it does. And it can interface with the separate interlocking also as well. So CBTC train location failures. Route locking shall remain in effect until the train is proved clear of CBTC subsequently. That means, let us say a CBTC train has lost its location. Until the train is detected outside, it is really route is kept locked. And if the secondary system detects, then it can be made use of. So responses to the point failures, loss of switch indication. So naturally, CBTC applies the pullback to the movement authorities, authority, whatever is issued earlier. Traffic direction reversal interlocks. Normally, whenever a reversal is given, all the safety conditions have to be seen when we are reversing a train, CBTC train. So there shall not be any opposite train. It's the same route locking sort of a, whatever conventional interlocking gives, all those conditions are proved here. Similarly, work zone protection also. Then similarly, broken rail detection. Actually, CBTC doesn't bother about broken rails. Auxiliary system is provided, and that auxiliary system can be integrated with the CBTC. So level crossing also. So if, for example, if a train stops just before the level crossing gate because of a station, then only after starting of the train, the advance indications are to be given, approach indications are supposed, warnings are supposed to be given. These are all the typical signaling principles only. ATO functions. Automatic train operations are starting, stopping, speed regulation. Then this depends on the passenger comfort levels. Actually, because acceleration and decelerations and jerk rates, they're all very important. So user specifies all those things. And all this should happen within the ATP over speed limits. So ATO cannot override ATP. Station stopping accuracy shall be as specified by the user. It is given in the standard also. So multiple ATO speeds CBTC should support. So platform berthing control. We have seen before also that platform length is approximately equal to train length. Unless the platform is vacant, it cannot go. And on the same platform, it is possible to plan for multiple stoppings also, like the air platforms. You can stop at 2 places also. We are talking about automation, actually complete automation, not driven by the persons. Door control. So it can be limited to automatic door opening, door closing, or both. Or it can be completely given to the control of the driver also. So the train doors and platform edge doors, both of them are interlocked. Unless they match together with a particular precision of the deviation, the train doors shall not be opened unless the platform edge doors are exactly to the same measurement. What we are talking, standard talks about practically interlocking of the train with the by the CBTC basically. ATS. ATS is actually train management system, and it is optional actually. Again, there need not be any ATS separately. In case one more, actually ATS is benefited by 3 characteristics, as we have seen earlier: precision of location, bidirectional data communication, and data processing. If the ATS features of CBTC and ATS features of a separate ATS also can be integrated, standard permits that. So ATS user interface, I think we will be looking in the next part also. So each CBTC equipped train shall be assigned a train identification actually. It is a very, very important thing. So it shall automatically track, maintain the records, display on the ATS software. ATS actually gets all the train related information. Then train routing is the main function of the ATS. It can be done manually or automatically automatically done for the CBTC trains. Other CBTC trains, it is not possible. So automatic train regulation, that means scheduling and headway regulation. These are the 2 options actually. Automatic dispatch function for the train identity, schedule, and actual headways between the trains are to be seen, and service strategies. And regulation is done by increasing the train stopping at the stations, running time between the 2 stations are controlled. Instead of sending train at maximum speed, it is controlled. In case of manual driving, driver is given the profile by the ATS. ATS says, yes, you drive to this particular profile. ATS sometimes may also advise the ATP to take a particular speed profile, like wet trail condition. It can suggest. Of course, at the junctions, if the 2 services are supposed to match, it is done by the ATS. The transfer of the train between local and express trains is there. So it shall match the local train arrival suitable to the express train departure. This is done by the ATS. Energy optimization is another portion of it. So functional requirements of ATS functions further. Station stop functions are 4 actually. Station stop at next station, it can display, and hold train at the next station, skip the next station, or door control and inhibit. These are all the parts of the station stop functions of ATS. Restricting the train operations, also part of the ATS, but they can be hazardous. like they have to be considered in the hazard, like stopping the train in between two stations, temporary speed restriction, blocking of the switch on the track. This is done at ATS. They have safety uh, implications, work zones like this. Of course, fault reporting also, there are two types of faults, critical and non-critical, and they are all critical are to be acknowledged. And the fault reporting is also done by the train. There is extensive fault reporting systems. Interoperability is not part of this spec. This is the thing. Now, why it has happened? Because basically the standard is prepared somewhere in 2000. And before that, 20 years before that, actually CBTC was existing for about 20 years. So it is not possible to bring everything into the interoperability box. That's why they have left it out. It's not like CBTC, where CBTC standards are formed and then people started working, developing the products on that. So that is the disadvantage of CBTC, interoperability problems. So we'll wait for 3-4 minutes and then start part 2.
Right, sir. 5 minutes break you want. Right, sir.
I think we will start. Now this portion has is a much smarter, much shorter presentation. Is about user interface requirements and recommended practice for CBTC system design and function allocations. Now, what are all the requirements given in the part 1? How they can be implemented by design, by system design. So first, let us see user interface requirements. It has, these are the classes available in this. Actually, I made this presentation so that when they look at this later, they'll be able to see what is available in the standard. So that's why I'm just skipping this. So 5, 6, 7, these 3 things I'm going to cover. Operations related user interface. That means this is something to do with the driver, what he sees in his man-machine interface, and at the ATS, what the person sees, and at the station, in case the wayside stations, what is supposed to be seen. Now let us see first train-borne subsystem. Train operators display. Actually, train operator is the word used for the driver actually in CBTC. So TOD is the train operator's display. Let us say train stopped at a station and no departure is permitted because still time is there, and train and platform doors are open. We can see this. Let us start from the left side topmost. Mode is automatic train operation. That means the driver is not driving it. It is a ATO. Docked means stopped. Dwell. That means dwell time is the one used here in CBTC is the stopping time at the station. So still 5 seconds is there. Depart, no. Then of course station particulars. And door side, left side, manual door open. And there is no neutral zone. And this is the distance to go, 0 to 1000. Now it is 0 because it is already reached. This is the type of thing. And you can see actual speed, target speed, and maximum speed also is displayed. And there are some other things we will see this. And it is in the train is in the forward motion. What are the mandatory displays? The standard says train operating mode is required, CBTC operational status is required, and the current CBTC determined time speed is required, and maximum authorized speed, and overspeed condition alarm, if at all anything. These are the mandatory requirements. Optional are so many, like we have seen there a lot of type, train type, station related, fixed territory type, then train run identity, train location, track designation, train length, reason for movement authority limit, why, like let us say the work is in progress ahead, that can be informed to the driver. Then target speed, speed profile to the approaching, when we are approaching the movement authority limit. So distance to an approaching limit. So these are all the things. Train routing through interlockings. Required brake rate to an approaching. These are all actually things which are optional displays. So many things. Level crossing status. Fault report, if at all anything is there. Any textual messages that can be sent from ATS. And time and date, like some train to skip next station or door status. Now, inputs to be given from the train-borne subsystems. So these inputs are given by the most probably the train operator. Operating mode selection, overspeed alarm condition acknowledgement, user login parameters. These are all, first two are mandatory. Next things are optional. Train length, train type, crew identification. Audible alarms, mandatory. Overspeed condition is mandatory. Optional are penalty overspeed condition, transitions into and out of CBTC territory. Then detected the parting, still it is optional only. Approaching work zone, train length conflicting, manually entered and detected are not safe. Now here, no, next one we'll see. Yeah, you can see here, actual speed is 70. You can see. Target speed is 50 only, this yellow triangle. Maximum speed permitted is 80, this red triangle. Because the train has crossed the target speed, that overspeed indication has appeared. So these are the type of indications. Similarly, the target distance shown in the table is there is a 1 kilometer is the next limit, and dwell time is 0. Now we can start. Departure, yes. Doors closed, disabled or closed. So there is a lot of information displayed to the driver, and depends on the optional. Many things are optional, depends on the, again, the OEMs who develops and who gives, and then most probably the users. So this is the information message or fault messages like speed warnings and over speeds. Those things can come here actually. So non-train borne subsystems. Non-train borne subsystems, as I have told, it is at the ATS station. So normally it is like our panel, VDU, fixed territory related information like track plan, location of stations, gates, train status, train movement authority limits, that is our like route locking, information related to restricted train operations like work zone, they can appear on the panel itself. Optional are a number of things like train status, fixed alignment related information like permanent SRs. These are all the things. What are the inputs to be given? Inputs to request and cancel routes, that is cancellations, actual movement authority limits and all those. Unless the input is given by the user, limit of movement authority cannot. So inputs to establish and remove the work zones, they are to be inputted here. It is like panel operation basically. So some of them are optional actually. Maintenance related user interfaces. Failures can be three types here, he says. On-time performance affecting the train. There is no performance loss, but some specific CBTC functionality has gone. No performance loss and no loss of specific CBTC functionality also. Maybe when there is a standby system available, everything is working all right, but standby system has failed. So the three varieties. User interface requirement, displaying of the data, that is maintenance related, the graphical representation of the CBTC system configuration, completely. And listing of the current status of subsystems, whether the communication failures or hardware failures, anything graphically. Then timestamping of the failure alarms, failure logs, and giving the physical location of the failed CBTC subsystems. Here the biggest issue is there are a number of locations these equipments are distributed. Then early warning failures, the predictive type of alarms. That is the end of that portion. Now comes the recommended practice for CBTC system design and functional allocations. So this is a very normal general thing. So in this again, the first three are very normal routine things. So we'll be covering this, each ATP, ATO, ATS functionalities, how data flows, typically, not completely, fully. So we have said there are only 4 subsystems basically. ATS equipment in the central place, train management system, it is a software. Wayside equipment, it is like electronic interlocking with which can make use of precision of the train location, and train-borne equipment which is available in the train, which implements the movement authority limits and automatically controls the train. Then data communication equipment. So these are the relationship: ATS equipment, train-borne equipment, wayside equipment. This is called zonal controller also. This is called car controller or cab controller. And this is the standby interlocking. This is the tag. Actually, it gives the calibration of the train, that they are the fixed landmarks, which is like Eurobalises. They are provided very nearer to the platforms and more in the approach and at the platforms also. These are the tachometers and accelerometers, both are used. And this is how movement authority components actually. This is the authorized speed, train location, 2, number 3, target of the point where it is supposed to stop, and this is supposed to be the ATP profile. Now, this is the maximum speed restriction. This is the place where train is supposed to come to stop, and this is the safety margin. So, ATS equipment, it can be there at central location and wayside also. Central location is, as we have seen, the EMS equipment, and wayside is the local panel. Identifying, tracking, and displaying of trains, providing manual and auto route setting capabilities, regulating train movements to maintain operating schedules. Wayside equipment, we have seen already, we have covered it a number of times. Similarly, train-borne equipment, what it is supposed to do. Then data communication equipment, it is located at central, wayside, and then onboard also. And it is treated as non-vital communication actually. Now, principles of operation. This is exactly what we have discussed till now. High resolution train location by train-borne systems, communication of the same to the train location and other train status data to wayside equipment, movement authority determination, communicating the same thing to all what we have covered till now. It is again repeated in this standard here in this portion because this is to be implemented. So, braking system, service and emergency brakes, propulsion system, both subsystem, PIS, passenger information systems, fault reporting subsystems, other train-borne systems. These are all the parts of train subsystems. Integration with other systems, when we are talking about it, CBTC system and interlocking, traction power, tunnel and station ventilation, passenger information system and security systems, backbone communication networks. Now, there are 12 primary functions actually for ATP functional allocations. They are train location determination, limit of safe route determination, like this, these 12. How these 12 primary functions are related is covered in the next. The relationships between the subfunctions. It is a subfunction. For example, train location determination is a subfunction. Now, how it is implemented? Now, subfunction name is given here. It is a typical table. I will show the next slide for another example. And description of the subsystems and whether it is mandatory, optional, vital, or non-vital. And then what out of this ATS, wayside, or train-borne or external, where it is supposed to, each function is allotted. What is this functional allocation? Subsystem providing inputs. These are the 4 subsystems. This subsystem gives this input. CBTC wayside is this to achieve this subfunction. And the subsystem performing subfunction. where it is executed. This function is executed by CBTC train-borne system. And who receives this output which is generated by the train-borne system is this. So it is a very good document, and of course this itself requires 3-4 hours if one has to explain. But it is a very transparent, very clear standard, what I have seen, a high-level document. If somebody can understand this, then it's a very good level of understanding of CBT C can be made. Determine the potential limits of movement authority. In this location of CBTC train ahead, it is a subfunction. And this is the actual description of that. Is it mandatory? Yes. It is vital? Yes. Now, CBTC train-borne system gives the input naturally because location of the CBTC train ahead. Subsystem performing the subfunction, CBTC wayside. This is done at the ZC, zonal control. Subsystem receiving the output, CBTC wayside as well as train-borne. So the explanation is given here that the wherever the clarifications are required. So like this, so primary ATP functions, what we have seen, all the 12 are given here and how they are related. So see each one up to 12. This is for train location determination, how they get related to each other. Each clause, subclause is given to have the clarification. This as a sample I am showing because this is beyond the scope of the presentation. So different type of like supervise, enforce, authorized speed and travel directions. Similarly, for ATO function allocation also, determining the ATO profile, determining the train berthing location, regulate the train speed, door control, train-borne display data interface. These are the 5 primary functions for automatic train operation. And how they are related, what functions they determine the train's ATO profile. If this subfunction, the subfunction is described here. This is optional and it is non-vital. Because ATO profile is not a safety. So like this. So similarly, ATS functions. There are 9 ATS functions actually. 9 primary functions: train identification, tracking, routing. ATS is nothing but TMS, automatic train regulation, station stop functions, fault reporting, all those. And their relationships are given here. And this CBTC operating train identification. So who are all involved in this? Which subsystem gives the input? Which processes and where it is given? So train identification is done from the train-borne system. Input is given, and ATS equipment decides or takes the train identity and it uses. It is optional and then non-vital. Data flow also, how it flows for each one. This is also very good section where very clearly it gives that as per this section, data from temporary speed restriction for that from CBTC ATS to CBTC wayside. That means ZC, wayside means interlocking. This is TMS. So how the data flows for temporary speed restriction, this subfunction generates the data, and this CBTC wayside receives the data. Like temporary speed restriction is entered by the user in the TMS, and that is taken by the CBTC wayside to decide the movement authority limit. Like that. And tens of them are there in the standard actually. I have just given a few things just to explain how it is to be used. So this is finishes the presentation, but there are questions and other things available. Actually, we can maybe spend another 15 minutes or so on that. And incidentally, my batchmate, Mr. Alam, is also available in this group presentation. He was involved. He is now the consultant for the Lucknow Metro. He was involved from the commissioning, now maintenance also he was looking at it. So some of the practical questions probably he will be able to answer. Of course, I have received a lot of messages. I don't know whether they can be dealt now itself, but I will be in touch with you people and to get the answers for some of them. We'll go to the.
I'm ready, sir.
Hello. Yes.
A small interruption.
Yeah, please, Shailendra, please.
Mr. Alam is celebrating his birthday today. And I thought,
Oh, happy birthday! Oh, he is not there with us.
I don't know. You mentioned that he is in the group, but I know he
Yeah. Yesterday we talked. He said, "I am not ensured. I don't know."
Please continue.
Okay. Maybe Venkatramana can look at it. Yeah. So then I think we will. This is my question actually. Nobody has asked. I am not expecting answer. It's
Sir.
not meant for. What I mean is,
Hello.
yeah, Venkatramana.
Hello.
I am able to hear you.
Sir, right, sir. Sir, the questions have been compiled and I put it again. I'm posting it back in the our chart box, sir. If you open the chart box, probably you'll
Yeah.
get the answers. I think 6 questions at a time I can able to post. It's not permitting more than that. So the first
Okay.
6 questions, sir, it has been given.
Before that, shall we look at those questions which came before when
Yeah.
that is better now?
Sir. Those questions are with you, sir?
Yeah, it's part of the presentation.
Yeah. So sir, actually,
for example, these are the questions.
yeah. Okay.
So
Okay.
some of them may be cleared. Let us see.
Please, sir. Please, you go ahead, sir. Sir, we received some questions while registering the application by the participant. So those have been handed over to a speaker. Samreddy sir has compiled, and I think he's going to present those things also. Sir. Please go ahead, sir.
So my question here, why I have asked this is, to the Indian Railways is opening up to new technologies and new systems, and then new product systems are coming up from outside. Unless the signal engineers are equipped with the knowledge of the international standards, it is going to delay the adoption. It is going to cause quality problems. So that is why I think this is a very, very important thing actually, that maybe reset a railway board, somebody has to think about it, because the standards, those things, they cost money. But maybe specific purpose, if it is taken, to how many people it can be shared. Can Indian Railways have an agreement with those organizations for unrestricted use among the officers or whatever at a particular level? That has to be seen. Only that is my intention. Yeah. Before going to the questions, this is one of the things I have seen on the internet. Bombardier, he has shown this. You can see the x-axis is actually the capacity tooled with, I think, number of people dealt. The y-axis is the speed. You can see the last one, we'll see blue one. When the number of people to be transported, that is mass transit, the number is more. the CBTC is treated as the preferred technology. Then at a particular higher speed, but the speed is less actually. For CBTC cannot cater for naturally for very high speed things because the headways are so less that you can't expect without discomfort to apply the brakes and accelerate. That is why actually the speed limit definitely would be there. Now at a little higher speeds, now ERTMS 3 is being expected actually. So I think that the commuter level really you have to see with little higher speed that ERTMS level 3 has an advantage edge. This is another thing what I yeah
sorry
yeah Shyamal please.
सर ये एक काफी 2-3 साल पहले एक बार बॉम्बे में मिस्टर राव है ना जो अभी अहमदाबाद मेट्रो में है, ही वाज प्रेजेंटिंग समथिंग. उस समय ये प्रपोज किया था, उस समय सीबीटीसी ऑफ सेंट्रल रेलवे में प्रपोजल चल रहा था एमआरबीसी की तरफ से. उसमें दे वर प्रोपोजिंग यूज open Wi-Fi frequencies of 2.4 gigahertz or 5.8 gigahertz for the backbone, Wi-Fi backbone. But I want to just listen whether we should go for that open channel or we should subscribe a paid channel from DOT.
Really, actually, as I have seen in some of those books, that today even LTE is being used. LTE also is being used for the CBTC purpose. Is not given the examples. The book what I have, the railway signaling and interlocking, what I that international compendium what I have shown, in that it is given that even LTE is being used. Most of the places this is Wi-Fi actually 802.11. That's what is being used.
Sambility Kashinath here.
Yeah, please.
I just want to tell you that this usage of free band, may be okay in the underground metros because you don't have any chance of interference with any other user who may also be using the free. But in elevated metros, most of the metros now are going to be elevated. It is better that, as Shyamal said, we should take
Maybe. Yes, definitely.
I heard there was some problem of interference in Cochin Metro. If anybody is there from Cochin Metro available in this discussion, he can highlight.
Actually, Lucknow, of course, Lucknow and Kochi must be with the same system of Alstom. Lucknow said there is not a problem, and then even Hyderabad Metro also using the same Thales. They also announced it, but definitely, yes. Open frequencies can be always sometime there is a risk
because you can't stop somebody from using it band what you already use.
That is right. When we are investing so much in the overall project, I think we should go for our own communication system.
SC Mishra decide. Actually, main problem with the open system is, as on date, a lot of industries, they use high power transmitters, which block the receivers in the metro. Similar case was detected, I think, found in Hyderabad Metro and other places. And a survey was conducted to find out which industry or which households they have high power transmitters in the open band. So that is one of the main. If they restrict their transmitted power, then obviously there will not be any effect because the switching of the frequencies is there. But if transmitter power is higher, then it affects the other operators.
It is a nightmare. Actually, you can't expect really searching for the signal strengths.
Yeah.
Really, yeah.
And Sambility Kashinath once again is regarding this interoperability. That is something. Now that CBTC is going to be so much widespread in all metros. And metros also, they are not constructing the whole system in one go. They make one line, then add another line, phase 2, phase 3, like that. So, if we don't have an interoperable type of CBTC system, a rake which is running in one section will not be able to go into the other section. That restriction, I think this interoperability should have been probably covered in the IEEE specifically. Otherwise, there's no purpose. of making
Yeah,
this.
it is a very big limitation for the CBTCs. But now we have to see actually even CBTC and then ETCS trains are going to share the track. I think in that NCRTC this thing. I don't know how it can be done. Some of the sections are shared by the CBTC Metro, some of the lines, and also the ETCS.
Going to be tough.
Yeah, it is a challenge.
CBTC it's not interoperable among the different vendors itself, CBTC itself. So how it can be interoperable with ERTMS?
Maybe some places it may be possible actually. See, like the standard very clearly says that it is possible, whereas interoperability between CBTCs in a limited way only, not completely fully. So CBTC is actually, it is a type of a market where now it is going to be very difficult to drive them for interoperability.
Because what they have done in ETCS is they have standardized the telegrams, which is exchange between the onboard and the fixed. Here we don't have any probably standardization of the telegrams or the messages or protocol for the messages which are exchanged.
What I have shown, it only says actually the relationships only. There is nothing specific. So we can't expect interoperabilities, I don't think. It is a decision to be taken really in the future metros also, when we are going to most probably intercity high-speed trains to merge with the local CBTC operated mass transit systems. Is going to be a big challenge and limitation. Yeah. Now this is what,
like EMRC, they have line 7, I think they have gone for CBTC. All others are the conventional systems. If they want to convert the conventional system to CBTC, it won't be interoperable. Unless you go for the same.
Yeah, people are talking about today and future. Actually, future is CBTC, ETCS combination. If it happens, we have to see until such time, next generation train controlling. Yeah. Yeah, one question is, if already electronic interlocking is there, is it possible to implement CBTC? Of course, it is a hypothetical question. Mainline, I don't think it is possible to go for CBTC, but theoretically it is possible. Local zone controller can take information, exchange information with the electronic interlocking, and block section we can have zone controllers controlling the trains. Theoretically, it is possible. There is no problem. That is the answer.
Kabiridi.
Yes.
I think in the specification itself, there are 3 types of implementation.
Yeah.
And in the first type of implementation, they are assuming some kind of interlocking can be separate from the CBTC.
Yes.
Where CBI, I think they are calling it CBI.
Yeah.
That is incorporated in the overall ATP.
Yeah, it is there. It is there. Yes. So that, the electronic interlocking can be used in the station for the purpose of route settings, route locking. Again, for the purpose of location of the trains in the station also, you have to go for CBTC type of detection system or train location system. Otherwise, you will not get the full benefits. So only interlocking portion can be taken out from the electronic interlocking. Yeah. How much improvement in headways is theoretically achievable with CBTC? How is headway calculation done in CBTC? Simulation studies done in IR for any section. Simulation studies has not been done, and this is the headways achievability of the headways and all these things is this. It is a system design really. It is a greenfield sort of a thing. If somebody asks, yes, I want to have a metro at so-and-so station with 7 stops or 20 stops in a distance of 10 kilometers, and I want to run with an headway of 60 seconds. Like that, it comes out, I think, CBTC. Now the CBTC design starts. How many zonal controllers are required? And like that, it starts. It is not really headway calculation is done like that. And these are all the algorithms actually, which are available with the OEMs. So we can't really make any comment on that. Number two, how is security of data transmission ensured? Okay, the presentations what I have seen for Hyderabad or Lucknow and these areas, it says encrypted data. It is a very simple sentence, but how safe it is, really we don't know. That I can't comment on that actually. Yeah, this we have discussed, being ISM band susceptibility to
Data.
Yes, it is there.
Data transmission is part of the ATP, and ATP has to be SIL4.
No, data transmission need not be actually, because automatic train protection, even though how safely the data can be, safety of the data insurance, if it becomes the end terminal's responsibility, then data communication network need not be SIL4.
Exactly.
That is the definition actually. So that way, the data can go to any media, any devices, switches and all, routers and all. Ultimately, there should be a very clear detection mechanism between the sending unit and the receiving unit. That's how the SIL4 is ensured in fail-safe communication systems.
Ready?
No, the
Yes, sir.
question is about encryption. The question is about encryption.
Yes, Aditya.
That encryption should be safe enough.
Aditya, this is an issue. The cyber security is an issue in every encryption area, and therefore now the new technique which is emerging is the quantum encryption technique for quantum networks, which already implemented Moscow and Centrifuga, so that it is not easy for anybody to hack into the system for any reason. Although the system is SIL4 and it will only fail on the safe side, nothing much will happen even if somebody intrudes.
Yeah. How effective is the inscription? Yeah, that is right.
The work is going on quantum networks for encryption, where hacking becomes more complicated, more difficult.
Okay. So some are simple questions only. How different is CBTC from TMS and CMS? I think you have explained. 5G technology in the CBTC standards. Standard doesn't talk about actual worldwide somewhere. The advantages of using is not much of it. Bandwidth requirements for multiple lines, Mumbai suburban. Yeah, this has to be seen actually. Basically, I think by reducing the increasing the number of zonal controllers, I think this problem can be solved to some extent. Zonal controllers, the number of trains that can be dealt with in a given area is the responsibility of the zonal controller. So if we have multiple lines, 4 lines, then we can use separate systems for each line, and where the trains are supposed to change from one pair of line to the other pair of line, there the JETSIs, zonal controllers can talk to each other. I think that can be, this is a hypothetical answer I'm giving.
This concept of line-wise zonal controller can be there. We have already sanctioned a work for Mumbai suburban section, Central Railway, and that for the Harbour line it was supposed to be done. I think MRVC is working on it.
Okay, sir. Okay. Now that way, I think the bandwidth and other requirements may not be a big practical limitation. CBTC and made in India products, that is left to the industry. Migration from ETCs, yes, level 2 to L3 or CBTC with manned trains. Actually, theoretically, practically nowhere CBTC tried the main lines. I don't think it is going to be really useful. Should be, I think ETCS L2 to L3 is a better thing. Frequency interference. Yeah, this question, how CBTC will be integrated with the Locotrol? Locotrol of GE, I think. Actually, CBTC and Locotrol, they do the same function in like fuel consumption, saving or other things. So only one can remain in the loco, both cannot do. CBTC or Locotrol, only one. Maximum speed is not very high in India. Why should we?
Can't we integrate Locotrol in the ATS?
Yeah, in ETCS.
I mean, not ETCS, ATS portion of the CBTC.
Yeah.
I think Locotrol can be incorporated.
Yeah, basically ATS has the what we call low energy consumption mode, and all is the CBTC's ATS it is having. Locotrol purpose also is the same. Locotrol also, that is one of the things I think, while coasting, that power is reduced automatically. The purpose is the same actually. CBTC's ATS and Locotrol. The purpose is same. So both cannot do that.
Yes, Locotrol is being used only on the main line. Locotrol is not being used on the metro anywhere. So
right.
Locotrol and CBTC are used in two different places. Locotrol on the main line, CBTC on suburban.
It is not required in CBTC area at all.
Yeah.
Because train are themselves sufficient and the train integrity is maintained. So there is no need for, and there are multiple powered itself in our suburban section. So the Locotrol is not required. It is controlled by one DT car. All the cars are controlled from one place.
Yeah. So maximum speed is not very. Actually, it is a medium speed. Actually, CBTC is suitable for medium speed, 60-70 kilometers, because frequent brakings and regulations, right? How to establish communication and open railway like suburban? Yeah, it is, communication is a challenging thing actually. Yes, because CBTC, I think most of the places it is underground. That is why I think it is not much of a problem have come up now, as Mr. is telling.
In open railway, one more problem will be there. The mixed traffic, you may have a goods train, you may have a typical train, you may have, and along with that suburban train also, like in Bombay suburban. So there it's going to be a problem to us.
Another thing is CBTC, because of its more resolution or accurate locating of the train, it requires a lot of trackside sensors. I don't think in the open line like Bombay suburban you cannot work. Very difficult. I don't know how interference can be taken care of. It's a big challenge.
I had, when I was there in the board, I had raised all these issues when the proposal for CBTC in Bombay suburban came, and they finally said that we will only go on the harbour line, because harbour line is exclusively for suburban. Other things will think later.
Okay. Yeah, I think that is the thing. Venkatramana, I think if time is there, you can.
Sir, another 24 questions are waiting for your this thing, sir. Actually, I'm posting 5 questions at a time. Just go through it, sir. As soon as there's 5 other, another 5 I'll be posting, sir. The same questions which are up in the chart, I compiled separately and then again posting for your convenience sake.
So shall I come out of this?
You can able to open the chart now, sir. This is the 6th icon from the bottom controls. The 6th icon, just you click on, sir.
Yeah.
Are you able to see now, sir? The last 1, 2, 3, 4 numbered. The numbered ones are your questions, sir. Actually, 5 questions I posted now. So another, I'll go on posting as soon as these questions are over, sir. Total 24 questions are there. Please, sir.
Which one actually it is showing? It is from you. Okay.
So these questions, the names are given on the top. Who has asked this question at what point of time? So if you above the question, it will be there.
Yeah, the CTP profile of a CBTC train takes into account the speed of train ahead.
Sir, able to see, sir? I mean,
From Akhilesh Yadav, this has come.
sir, you're able to see the numbered questions, sir? 1, 2, 3, 4, 5?
No,
The chart?
I'm not able to see the numbered questions.
Oh.
Yeah.
Venkat, you can post on the screen.
Okay, it is in the last.
Sir, otherwise I will post on the screen, sir. I will
You will
take the
do the others
presentation.
also.
Yes, sir, I will take the presentation. I will post it on this one, sir. So in presentation.
I will stop sharing.
Yes, sir. Please stop sharing, sir. I will post it on this one.
Yeah.
It being recorded, Venkatramana?
Sir, it is being recorded, sir. The entire proceedings are being recorded, sir.
You will send the link later on.
Yeah, sir. It requires some processing, so it has to be converted into MP4 format, sir. It takes some time. Yes, sir. I will. If whoever wants it, I can share this link. Otherwise, I can keep for some time on the RESET website, sir. So these are the questions, sir. Somebody, sir, able to see this my screen, sir?
Yeah.
Yes, sir.
Basic requirements of CBTCR.
Sir, still I increase it this one, sir. Probably the first one will be I think like a statement.
Yeah, it is statement. Second one is in
Sir.
degraded mode of operation.
Sir.
What are the safety considerations?
Sir.
Yeah. I have shown one screen, I think. In the degraded mode of operation, the train location is lost basically. So the train location is treated as the occupied portion of the full track section. Hello. In case we are using, let us say,
Sir, you have to unmute your mic, sir. So kindly you have to unmute your mic.
Yeah, sorry.
I'm sorry. No, sir, actually, we muted all because some noise was coming. So he was also
Okay.
not muted.
Oh, yeah. In degraded mode of operation, what are the safety considerations? Basically, in the degraded mode, the train detection, let us say train location detection, if it is lost, then the auxiliary train detection system of axle counter or AFTC, if it is used, the safety is ensured in such a way that the movement authority limit will be to the border of the track section. That's how the safety consideration, that is the main safety consideration actually. Rather than if CBTC were working, this limit could have gone up to the train actually. Instead, it stops at the auxiliary train detection system limits. That is it. Interoperability of various EAs can be deliberated. This is a big challenge. Arvind Saxena Saab should tell really. This is becoming a big challenge for ETCS2 also. Yeah, this is.
There is a work going on for the U-links, which is called making the entire thing standard for all interlocking and the interfacing standardized. That's how many years it will take, but that is the problem and that is the challenge.
Yes, sir. Yes, sir. That is a big issue, really. Next one, any dedicated frequency spectrum required for train control communication, wayside station computer rather than using the free. Yeah, it can be used actually. Like as I was telling, LTE is being used. I don't know, LTE they might be using for backbone. I don't know, for moving train. 5G should be a good this thing really, because its area of control is gets limited, and that should be offer a very good alternative for all this 5G. I don't know, Mishra ji or anybody can throw some light on this.
Sambir Reddy sir.
5G is, I think, the better thing, na?
But it is far, far away.
Far away. But
It
Chinese
can be,
railways,
yes.
Chinese railways have started because it is better to work on a thing where development is still in taking place, so that our interests are taken care of. That.
I think UIC, etc., they are working on this, but latest I don't know.
But in Chinese railways, actually, they are using 5G that they have conducted trials in IRSC news must also seen.
Yeah.
To download the diagnostic data as the high-speed train comes and stops at a halt station, within a minute or even less than a minute, the complete diagnostic data of the train is downloaded by 5G technology.
Yeah.
That's the one. Yeah. So
it is possible through 4G also.
yeah, it should be.
Diagnostic data dump is never very big.
And we don't know how much big it is. High-speed trains, not so many parameters, so many sensors would be there. So dedicated frequency spectrum is required. That's what everybody, one of us may ask. Really, which one? I can't say. Train localization by GSMR is enough when and skidding etc. cover up needed. But really, the one single system for location finding cannot be, I think, relied upon. Nowhere, I think. So the tachometer type of a system, odometer system, shall continue to function with fixed balances, correcting the location errors caused by the skidding, slipping, and wear of wheels. I think that is a quite reliable and known system. I think that should be there.
CBTC is not, I think, relying on GSMR nowhere. Mainly the location correction through the fixed bellies and incremental through the tachometer.
Yeah. In fact, a secondary thing, they were using some laser sources as a odometer and even accelerometer, everything.
It can be RFID, something like that. Similar,
Yes.
I think, to exactly pinpoint the location and correct the locations.
Yeah. No, I think conventionally railways are not experimenting much with communication technologies. I think we are the one which we have done Indian Railways, this TCAS is a very good example of making use of the simple technologies. Yeah. Next one, what is the present status of GTC? No. Secondary train detection is supposed to be optional. Then why do all projects still use it and are aware of the CBTC project where secondary train detection is supposed to be optional? That's what actually, the less equipment is not the right statement for the advantage of CBTC. Because once we say the mass transit, we expect its availability up to 99.99999. So we can't depend on just CBTC alone for localization or for the purpose of the train detection purpose. So that is why even at the degraded operation, we will be able to do some services. That is why I think
Hyderabad is having this secondary detection system.
Yes, a secondary detection systems with pakka auto signals.
Fallback system is normally used.
Fallback. But only Mumbai I have seen. Yeah, Mumbai I have seen the line 3 train detection system is there, but signals are not there.
Okay.
Signals are not there. Train detection systems are there.
You
Yeah,
are
that-
talking about line 1, present working metro?
No, line 3 actually. I'm
Acha,
talking
line
about.
3. Okay.
Future, line 3. And that is also sufficient, I think. But only thing is for that, it takes care of only train localization failure only. ZC failure and all, it cannot take care.
Exactly. When there is a complete failure of the CBTC, then
Yeah.
axle counter with the signal, you can run the minimum train.
Just like auto signaling.
Yeah, just like auto signaling.
With some maybe protection. Yeah. Does the IEEE standard give any requirements for interoperability between equipment? No, actually, they have said very clearly that it is not at that stage. Not. What are the subsystems that need to be SIL4 to have the whole integrated CPT solution to be SIL4? I think automatic train protection system. That's all. That's the only thing that has to be SIL4.
No, automatic this emergency
works,
braking.
no?
Emergency
Everything
braking is also SIL4 in the trains. It is a must.
Yeah.
Part of ATP.
ATP consists of ZC and then CC. So both together, na? Train also. Train mein.
Train is separate, but train emergency braking only is SIL4. Door closing, etc. Service braking is SIL3 and SIL2. But emergency braking is SIL4.
Yeah, that is why if we look the things as functionality wise rather than hardware wise, it can be clear. So ATP functionality of CC shall be for SIL4. Carborne controller does both the functions. That is ATP protection as well as ATO protection.
Yeah.
So ATO protection, ATO can be maybe for SIL2 or whatever.
ATO is not SIL4.
Yeah, ATO need not be SIL4. But actually now the one what we have seen Nippon signals. They said it is their system is for SIL4. We can check actually how which portions are evaluated for the SIL4 purpose. I think it is the emergency braking only the thing which can be for SIL4. Does the ATP profile of a CBTC train take into account the speed of the train ahead? I don't think. It can't. It need not take. Because that is again a hypothetical thing.
No, not. It is not part.
Yeah, it is not part of it.
No.
Yeah. What are the safety considerations for operation of a non-communicating train? Yeah. Non-communicating train, what they are trying to do is actually that particular section is treated as occupied, and the track section where the secondary detection system is provided, and the trains are not allowed onto that thing, and the train is treated as, it is like our piloting system. It is brought to the station, like the piloting systems. Exactly.
Puneet, can you give some details on the failure of the trains, ATP in particular train? Puneet is the head of the signaling in Hyderabad Metro.
Yeah, okay.
Good morning, sirs. So actually, sir, regarding this, there are also actually doubts because we have discussed about this wayside system, secondary detection system. It's an optional system. Actually, if this is an optional system, then there is one mention was there that either the secondary detection system or the SOPs, like manual SOPs, can take care of non-communicating trains. So, so actually, we have to think of like Also it was discussed that in Mumbai that we have taken away from the signals, but still having the track circuits for the secondary detection. So I think track circuits will still be required in case we have to go for the failed CBTC train. That is the minimum requirement. And regarding the failure of the trains that we have here, we had actually many issues of the onboard failures earlier, where we had which were related to basically interface. We issue some door enable signal for each and every station stop. So there was some time lag, which was 1 millisecond was given. So that has been actually earlier it was 500 millisecond. Now it has been increased to 1 second. Definitely all these safety checks have been done. So it has reduced a quite number of VOBC failure. So we have many failures like VOBC on the run was getting passive. So such kind of failures we have reduced by almost 60% by way of this simple change.
Puneet ji, one question on this. This 1 millisecond starts a few milliseconds to 1 second. How the first decision was taken, there must be some precedence. Somewhere we must have followed something, whether is the systems working elsewhere and it is not working at our place?
Actually, it is likely to be like this because it is basically the interface between the signaling and rolling stock. So it was thought that it will work here, but when it was resulting in the failures, because this system being the channel comparison, and when the channel comparison was failing, the system was halting. Yes.
Oh.
I see.
How is train integrity, train running as one unit, not parted, is managed? Because both ends of the trains are supposed to give their location. The algorithm is built on that, actually, most probably. I am not really aware of the exact this thing. The algorithm. Because when the two trains gets attached also, and if some input is given into the system, and which if it is wrong, and it clearly detects and then says that the length is this.
Train integrity and parting is like a failed train.
Yeah.
It is treated like a failed train.
Actually, there is one of input that we receive for the onboard computer. This train integrity test is received, and it is one of the train line. And we have the structure like in both the driving cabs. We have the onboard computers, and both of them are linked with the train lines. And if this train line becomes low, which means the loss of the signal, and the system takes the safe reaction in this case. So it detects the train integrity in this way.
Okay. Okay. Next question. What is the reaction of a CBTC train when communication from track side is lost? Does it continue the last revived MA or EB is applied? I think there is some time limit. There is a time limit. If within that time, if the communication is established, I think it makes use of that.
Yes, actually,
there is a delay. Puneet, you can go ahead. If there is a delay in communication, train will not move.
Yeah.
Right, sir.
Yeah.
Emergency brake is applied. Yeah.
Right, sir. From the moment the train communication is lost, after 3 seconds, the train is treated as non-communicating train. So basically, 6 telegrams in the 3 seconds, it can miss. And because then the safety envelope takes care of this 3 seconds, 6 telegrams means 500 milliseconds. And then at 12th second, the EB is applied. So this 12 second is the time limit for this.
Okay.
Actually, this is the main problem with open system. Whenever at some places it was found somebody is transmitting high power and receiver is getting muted. So there was no communication and emergency braking was taking place. I think it has happened at some places.
Okay.
मिश्रा तुम कहाँ का एक्सपीरियंस बता रहे हो?
हेलो, नहीं यू विल फाइंड, मुझे एग्जैक्टली याद नहीं, इंडिया में हमारे ख्याल से दिल्ली मेट्रो वगैरह में कुछ केस हुआ था किसी इंडस्ट्री में उनके लोकल जो यूज करते हैं वाईफाई ने, दे हैड इंक्रीज देयर पावर, तो somehow somebody with the power meter they traveled along with the wire duct and they localized ki somebody is transmitting high power. They contacted them and then maybe ki some locally made Wi-Fi or some power amplifier, something they were using. This is part of some research report also.
Now, next question is how slip and slide control affects the CBTC capacity. Generally, it should not affect, theoretically, unless because of slipping and sliding, too much of many times happening to that particular train, it can affect. Otherwise, data, I don't think it should affect.
In fact, slip slide control is one of the critical control system of the rolling stock, and it is I think some SIL 3, SIL 2, something like equipment which takes care of the slip and slide, and probability of slip slide, what we think is taking place, it is not there. It is too less, and it is not to an extent where it can affect the.
Okay.
This question comes from the experience of the TPWS implementation on Southern Railway. Slip and slide was creating some problem initially when TPWS was being implemented.
Okay. How variable train lengths are managed? Does the driver need to input any parameters? I think it is theoretically it is not required because both ends of the train they are supposed to give their location, so it is not an issue actually. 16. Why speed is shown increasing in A and B parts of the braking curve? That one because it is expected that the train is in fact. The train is something like losing control, sort of a thing. Its speed is increasing, going out of control beyond the emergency. That's why it is shown like that, and it is a very enlarged thing. It won't happen like that. Whatever A, B, C, D, A, B, C, all the three shown can be in less than 1 millimeter. Actually, if we look at the normal graphs.
No, sometimes there is a possibility also. A train is going to the down gradient, and even there is no power, there is a possibility of increase of this.
Runaway train with a down gradient. Train localization by GSMR is enough. Then why wheel and wear skidding cover up needed? That we discussed, I think. Few optionals are mandatory as per Metro GR. Mishra ji, what is this? Few optional.
I raised while you segregated two requirements, mandatory and optional, as per IREEE requirement. But our GR, in fact, put some more restrictions. For example, ATP failure, they have not defined exactly what is ATP failure. So if a distance to go is not available, it is taken as ATP failure. So there are some mandatory requirement or as per our Indian Railway GR. Which is not covered in IEEE. That's what I indicated.
Yeah. As per my last knowledge, it's still in technology tendering stage only. Which one? 19. We don't know which place is it. Mr. SP Singh. I think there is no ballast in the CBTC system. Yeah, there is no ballast, but a different type of fixed things are used, which gives the whatever is the 900 megahertz or whatever. That is there coils actually basically different. It need not be Euro values, but fixed location things are available. Yeah. Item number 21. Throw some light on fallback arrangement in CBTC. I think we have discussed sufficiently. 22 is considered to be more suitable for metro working. Will be having similar speed and braking. Will it be suitable? Yeah, CBTC standard says that variable brake characteristics trains, different type of trains also should be, technology shall be developed. Standard doesn't mean that it is achieved. Really, CBTC is not meant for really for mainline, what I think. Very clear.
We can say it is equivalent to ETCS level 3. Almost equivalent.
Yes, today.
Yeah.
But even level 3 itself is not fully matured. Na?
But level 3 is working in Sweden for last 4 years without anything.
Yeah.
And they say ki cost is 50% of the conventional signaling. Though they are using for the goods line, long stretch, last 4 years.
Even Switzerland, it was there, no? Switzerland, long time back.
But oldest, I'm telling you, more than 4 years.
Okay. So, definitely CBTC is not meant for the mainline, at least for India, with so much of equipment to be deployed. I think the main thing is that the resolution being asked is not really required so much. Let us take a goods train. Why should we detect it with 2 meters, 3 meters accuracies? It's not on the main line. Not meant for it. Yeah. I think Venkatramana, anything more are there? Oh, that. Can this system be used on the main line? Has it been commissioned anywhere? I don't think. Mainline nowhere. CBTC has been approved for implementation on the. Okay, yes, sir. That you have told. Cab to cab train communication has also been used as an. Oh. I don't know, sir. Really, cab to cab communication also is not there. CC won't communicate with another CC.
It is a train line which was mentioned by Puneet Arora.
Yes, sir. Failed train.
Cab to cab communication is part of the implementation type 3, which is called the train centric implementation.
Okay.
I think Alstom is already having a model based on that.
Okay. And 26 in MTR, there was case of side collision in CBTC section, which occurred while testing just national emergency brake console for. Yeah, this has occurred in Hong Kong. Hong Kong while implementing switching over of one line to the other, out of the two computers, one computer. It is, I don't know, maybe similar to our CKP division accident, main and standby switching over. It came in about 4 months back, a very clear article in IRSC News technical magazine, how this accident, side collision has occurred while implementing the CBTC in Hong Kong Metro, switching over. That can be studied, yeah. This wayside radio is capable of giving the exact location of front and rear radio on multiple lines, say. It should give like a Nippon thing if we consider There should be technology. We have to see actually. I can't, offline I can't answer this. Yeah. So, Venkataramana, any more questions?
That's all, sir. Sir, with your permission, can I conclude the session, sir?
Yeah, from my side,
Yeah.
it is over.
Yes, sir.
Yeah.
So, participants, any more questions from your side pending? Shall I conclude it? Sir, if there are no questions. Sir, thank you very much, sir. Thank you, Shri Samreddy Garu, for introducing us IEEE standard CBTC and covering whole gamut of signaling computing technology, especially ETCS as well as CBTC, and people trying to draw parallels between these two technologies. But I read somewhere, sir, these two never going to merge because of the vested interests of the CBTC lobby. And
Yes.
it is already developed, and then huge market is there in the world. And ETCC has come later, and then it is a governing body like European Rail Agency, ERA, and also the industry has come together in the form of UNISIG, and then they agreed for the interoperability. But whereas I think my perception is concerned, the CBTC, it will be a proprietary technology. So IEEE standards gives the functional requirements, sir, but it doesn't enforce the interoperability issues, sir. And I'm also very thankful for our speaker's patience. It is almost 3 hours, 2 hours 45 minutes, and also handled a lot many questions. In fact, the 70 questions which were raised by the participants while registering their participation. So those I compiled, and then he has answered in consolidated way, and also the individual questions also have been answered, sir. Thank you very much, sir. And at the outset, I also thank all the participants for their active role, and then making it very interactive and then lovely. And sir, we look for more such technical interactions in the future. A series of talks we are going to plan from the ERSET side, sir. I thank one and all, sir. If I miss something, excuse me, sir. Sir, anything if you want to say from your side?
One thing, really,
Sir.
I have made one comment that teaching is the best way of learning.
Yes, this is where to put
I have learned a lot actually today, and for that I have to thank Shalendra and you and all the colleagues who has interacted in a very nice way. Nice, it's very good.
Sir.
Thank you.
Sir, very
Thanks a
nice,
lot.
very nice.
Thank you.
Sir, thank you, sir.
Thank you everyone. Thanks a lot, sir.
And also the participation has gone up to the 120, sir. Around 210 people have registered, and then 220 it has reached. In fact, at one point of time, what I've done is I locked the session so that the interference will be less. But there's a lot of demand. People latecomers, they came later. So it is the stable people were around 98 people all the time, and then it has increased to 120 at what part of time, and has come back, sir. That is about the statistics. Participation is concerned. It's a very successful presentation, sir. Sir, I request Goel Saab to say 2 words.
I wish to thank Samreddy sir. Always a pleasure to listen to you. The session also has been very engaging, very useful. The participation is very good. I will continue with that. Thank you, sir.
Thank you. Thank you.
I also thank all the participants, especially seniors, Mukla sir, and seniors who are also there for some time.
Your voice is muffling.
Sir, your
Michelle.
voice is slightly mic, sir. Kindly, yeah, adjust your mic, sir.
I just want to convey my sincere gratitude to all the seniors, including Saxena, Chopra, and others, who practice the session, who have been giving guidance to the session. Youngsters at different part of the country, now University of Patna Railway, I could also notice the University of Palghar, our objective of reaching at least corner of the country, that is the result. I assure each one of you that it will continue to work for purpose in the time to come. Thank you. Thank you very much.
Thank you very much, sir. So with your permission, I will close the session, sir. Is there
Yeah,
anything
thank
more
you.
to say? Right. Sir. Okay, sir. Thank you.
You can conclude it then. Thank you.
Yes, sir. I'm closing the recording, sir. Just I'm closing, sir. Closing the session.